In this instructional video on organic chemistry, we will build molecules using the Snatoms molecular model kit. And so the purpose of this is to start building the alkane functional group, which has a general molecular formula of CnH2n plus 2. So we're going to start with one carbon atom, which is shown here as this black ball, and it has four smooth-sided surfaces, and embedded in that is a magnet. And what we're going to do is bond to those positions one of these white balls, which only has one smooth side. So when the magnets bond, you'll hear it snap together. So what we've done is form a carbon-hydrogen bond, and now we have 1, 2, 3 more valences to form hydrogen 2, and this molecule is the C1 alkane known as methane. And so it shows the tetrahedral geometry as a result of the sp3 hybridized carbon atom that allows 1, 2, 3, 4 sigma bonds to hydrogen. So if we move up to the next higher homologue of the alkanes, we're going to have ethane. And what we're going to do is substitute off one H, so we'll pull that off. We're going to put another carbon atom on. So now we've formed a carbon-carbon sigma bond. And then we note there's 1, 2, 3 open valencies that we're going to bond hydrogens to. So now we have a model that's C2H6. And again, that follows the general formula of CnH2n plus 2. So each carbon atom has 3 hydrogens, and we note that the central sigma bond we're able to rotate around. So there's free rotation. There's also free rotation about the carbon-hydrogen bonds. And in another video, what we'll do is look at the rotations about that in a Newman projection, where we're rotating down the axis. So this is the C2 alkane ethane, and if we take off one of these hydrogens and we substitute it now for a third carbon, now we have 1, 2 sigma bonds, and the remaining carbon here has 3 open valencies for 3 hydrogens. So now we have C3H8, and this is propane. And so again, if we count all the sigma bonds, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds in propane. And so now there's more rotations we can do, and again, in another video we'll look at conformational analysis with Newman projections. But for now, we're just building up the alkane homologues. So we're going to take an H off and substitute it here. And so we have the 3 open valencies. And so now this is butane, which is C4H10. So we have 3 hydrogens, 2 hydrogens, 2 hydrogens, and 3 hydrogens. So this is butane. And with that molecular formula of C4H10, it's actually possible to make a constitutional isomer of that, where when starting with propane, what we did had substituted off the terminal carbon, but we could also substitute an H from the internal carbon. And if we do that, we now have this molecule, which is a propane derivative, because the longest carbon chain is 1, 2, 3 carbon atoms. At the 2 position is 1 carbon, so 1 carbon is methane, but because it's a substituent on the longest chain, we can call it methyl. So this would be 2-methyl propane, and that is a constitutional isomer of butane, which again we had made by substituting off the terminal. So as we get above the C4 count in alkanes, we will see that we can have linear, so this is a linear alkane, or we can have constitutional isomers which are branched. And as you see with the branched ones, these overall tend to have a more compact shape, almost like spherical. The way I like to explain it is this sort of more resembles an M&M when it's branched. And when it's linear, it's more like spaghetti-like. And that has implications on the physical properties of the molecules as well. So we can go ahead and take off a terminal hydrogen, add a 5th carbon, and so that's going to add 3 more hydrogens. So now we have 1, 2, 3, 4, 5 carbons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C5H12, and then this molecule is called pentane. So again, it looks nice and spaghetti-like as it moves around. And so we can draw, or we can make an isomer of that, where instead of substituting from the terminal carbon of butane, we substitute an internal hydrogen. And so now this makes, rotate it around here so we can speak from left to right. We have 1, 2, 3, 4 carbons. It's a butane. At position 2, there's 1 carbon, so this is 2-methyl butane. And again, this would be a branched isomer of the linear pentane of the same molecular formula. So we can find that from this branched butane derivative, we can also make another constitutional isomer of the C5H12 molecular formula, where we're going to take off a terminal carbon, so as a methyl, and then we're also going to substitute it now on this 1, 2, 3 carbon chain, so it's a propane. At the internal position, carbon 2, we're going to take that hydrogen off, substitute it for that methyl, put the remaining hydrogen at the terminal now. So we have 1, 2, 3 carbons, so it's a propane. At the 2 position, we have 2 singular methyl groups, so this is 2,2-dimethyl propane, and this is a branched isomer of the C5H12 molecular formula. And you can see that this is definitely now being more compact as a constitutional isomer. So again, the M&M shape. So again, up until C1, 2, and 3, you can only make 1 isomer, but when you get above 4, you can go from linear to branched when you're talking about the molecular formulas. And then from there, you can start learning about the names as you go from the linear to the branched. You start putting the groups on the internal carbons, and then they're called substituents. So this exercise of model building and figuring out names will help you learn the vocabulary of organic chemistry as we start talking about carbon counts, nomenclature, and in another video what we'll do is build these models again and talk about uniqueness of the carbons and hydrogens and how that concept applies to NMR spectroscopy.